So this topic now is they call this funny wording 3B delta S for specific processes. Okay. And they give out a few examples, and the first one is actually you already talked about before, which is let's say if it is an isothermal volume change, let's say expansion as an example, which means initial volume to the final volume. And it's an isothermal, so it's initial temperature, final temperature is same, and we call just so simple as a T. And this one, I don't need to say whether it's a reversible or irreversible. So what I'm saying is for both reversible and reversible, we can calculate delta S for this process. And you remember the last lecture, I drew the table and to talk about this. And the reason that I can say it is, regardless whether it's a reversible or irreversible, I know my initial and final temperature, and initial volume and final volume. Right? Once those two states are defined before and after, I don't need to really know what happened between just the final state minus initial state. So that's what I can know. And in the textbook and all the books are taking the advantage of reversible process is something that I can easily calculate Q reversible. Makes sense, right? And from using that, I can calculate Q reversible divided by T is a delta S. So then the delta S can be calculated for reversible, and you justify, well, this one is the same. Even for irreversible, because your initial state and final states are well defined, so this should be the same. You should get the same answer regardless of the process. The path that it took is in this way. So this is for the last time I'm doing the same thing. So think about it. du is q plus w, and then I'm just saying that, okay, let me just take the advantage of reversible process, and because it's an isothermal, it is 0, ideal case. So from here, isothermal expansion for this, you guys remember the work reversible? Remember that? Minus nRT df dr. Remember that, right? So that's the one. So what I need to do is, okay, that should be an opposite sign of the Q reversible. So once more, this is I think I tried this one before, so negative of work. And so it's an nRT volume logarithmic volume differences, and then I'm going to just do the T here. T, and this term becomes my delta S. So my delta S is now nR. So I have an exact equation. Whether the process is, as long as the process is isothermal, now if I know the volume change, this is something that I know. As a side note, sometimes people give you the pressure differences for expansion and compression. The relationship of volumetric ratio is inverse for isothermal process, so it's an isothermal process. So this is quite a nice whether it's reversible, irreversible, I do have an equation that I can use and predict the entropy change. Number 2, and this is actually to me the most kind of practically relevant for, and this is what we call delta S for phase change. So once again, if delta S is Q reversible over temperature, and there you already know there is a one process that is actually involving with reversible heat, keeping the temperature constant, and we can call that one as a delta S, and that's for the phase transition. So for example, if you have a gas going to a liquid going to gas going condense into the liquid, they go back and forth, and the Q reversible here. How do we call this Q reversible in this process? Q for, I want to call, let's say, vaporization. Right? This is a vaporization. So what's my Q reversible here? Go back and forth. You do the notation. Heat under constant pressure. Right? So what do you call? What kind of symbol do you want to use? Delta H. Right? So delta H, and then you want to specify whether it's a vaporization, sublimation, or melting. So in this case, I'll just call it vaporization. So that part is a good clue. What about the T in here? Boiling temperature, right? Vaporization temperature. You guys can call whatever you want. Vaporization temperature or boiling temperature. So therefore, this is an example that I wrote. When liquid goes to gas, that's a vaporization process. Delta S for vaporization, which is a reversible heat, must be an entropy change. Vaporization. Heat. I'll just call it all boiling temperature. Okay? This is also boiling temperature. So to me, when I took my physical chemistry back in old days, yeah, certainly I remember that, but probably 5 years later, I forgot everything. But except this equation, I do remember. It's a very useful equation. Conceptually straightforward. This is a reversible process going back and forth. That's what the phase transition is about. And it happens at fixed temperature, so you just have to put it in this relationship. That's the one thing. Okay, so the third one is delta S for temperature change. And so we're talking about initial temperature to final temperature. So if you think about it, I have a system. I'm increasing my temperature. Let's say this is your boiling temperature. And according to this, if I draw the entropy, okay, and entropy temperature goes up, it went up, and then it will be this continuous jump. That is represented by this, which is if I talk about this is a liquid and is a gas, and then they continue to rise. Okay? And this must be a gas here. And empirically we know that temperature lower than boiling temperature is a liquid, is a gas at higher temperature. And if I just graphically understand this, there is some discontinuous change, which is delta S for the vaporization. And then they continue to rise. So they want to talk about, okay, what about this portion versus that portion? This, when you change the temperature, how can I calculate that? And you just have to use the same thing. So the delta S, which is initial temperature, final temperature, Q reversible over T. And I'm just using the same equation now I'm just trying to figure out how can I deal with reversible heat when I change my temperature. And this is under constant pressure situation. So do you remember what's my Q reversible under constant pressure? Once again, this one. Q CP DT. Guys remember that? So I can plug that in. And then all of a sudden I got this equation. So if I have a constant process, that will be this. And if I have a Q with CV dt, somebody said, well, we are doing in a constant volume process. And that will be the equation that I need to plug it in. Okay? So that is the one that's going to be the second term that will be showing up. So what that means is delta S is initial temperature, final temperature, T over Cp dT, or initial temperature, final temperature, Cv dt. Depending on whether under P is constant, it's easier to deal with heat as the Cp heat capacity of the constant pressure, or this is on the constant volume. And so it will have a different form, which is a Cp natural log final initial. It's the same as Cv natural log final initial. So that's how you do it. So I start to give you a sense about this when we say in the beginning of a specific process. Do you remember this is a volume change or pressure change? I guess that's on the isothermal process, right? And then this one is actually when you change the temperature from here to initial to final. You have two options, whether you choose on the constant pressure or constant volume. So those are the one that coming together. And I'd like to have a summary slide on this. So I don't know why textbook kind of organized this way. This is more like, to me, for phase transition, this one is a self-standing subject that you can always get to know. Entropy change for the phase transitions, vaporization, melting, sublimation, you just put that delta H over divide by the transition temperature, and you can calculate delta S. Whereas anything that's changing the volume, right? You're changing the volume, changing the pressure, changing the temperature, right? So these are the quantity that we can consider. But the reality is we cannot change three at once independently, right? We gotta just pick two, and then we're gonna summarize that process in a more graphical way. That's the one that I'm gonna talk about in the next section.